And now it's my personal delight to introduce to you my good friend Carl Maesak. He has been a Perl 6 application developer since 2008, so long before the actual release. When he doesn't write ecosystem programs, he also contributes to Rakudo and the Perl 6 specification. He has submitted over 1,600 Rakudo bug reports. And without further ado, Carl, please.
Thank you. It's wonderful to be here. Nice to see so many faces as well. I have 2 talks on this conference. This will be your regular philosophy talk, and then we'll talk about real, actual software that actually exists tomorrow. I'd like to start here. I'm a father now. Yay! Now you applaud as if this was some great achievement on my part, actually. Anyway, there is some connection here to the actual talk, so I wanted to describe to you a quick overview of our apartment, which is something like this, fairly standard. And this is how I've thought about the apartment all the time, basically, until the baby arrived, when the apartment suddenly turned into this. And what's not obvious here is that it's actually kind of a very factory-like environment nowadays. So you have your various pipelines and chains going through. There's some kind of food-related chain here, and then it ends up in the bathroom. There is some kind of baby amusement and baby rest cycle involved as well. And it's all cyclical, and it's all sort of centered around resources. And that's basically what led to this talk. It kind of made me think. And hold on, let me reset the timer here. Yeah, let's do it like that. There's a timer on the slide, so if I reset it, I have an approximate sense of how much time I've used up. It made me think, what is software development? Sort of, what is it that we do all day? And what kind of models do we use to think about the software development? And yeah, how do we relate to it? I realized when starting from this view of the apartment as factory, that I actually go around nowadays carrying 2 views of software development. And they're quite contradictory and at odds with each other. One of them is very bottom-up and very clean and nice and a happy place to be, and I'll describe that one. The other one is messy and ruthless and kind of both depressing and menacing and all hope is lost kind of thing. And so I'd like to explore these 2 views together with you. So I thought, yeah, that could make a decent talk. Hello, I'm Mäsak. I write Perl 6. I write Perl 6 professionally, which means something like I do it as part of my work. I don't know how this happened. I don't do Perl 6 all day at my work, but it's definitely a big part of my job and our job, and we're hiring, of course. I also do Perl 6 as a hobby and in my copious spare time as well. Yeah, generally I really like Perl 6. This talk is not particularly about Perl 6, though it might show up somewhere, we'll see. Instead, it's about these 2 views of software development. And I've been trying to find good names for them and a way to contrast them. And I'm hoping I don't overload my audience by basically having here today 2 very contradictory messages to you. One is that things are really nice and extremely hopeful, and one is that all hope is lost. So the first view is the sense that we as developers are in full control of the code that we're writing and the systems that we're designing. It's this happy place when you design something with complete clarity and everything works out really nicely, and you have your model and the software actually follows this model and does what you wanted it to in the first place, and all the tests pass and everything is nicely separated and dependency injected, perhaps, we'll get back to that. And basically some sort of the um, the success and the vanquishing of rational thought over the rest of the world. Uh, and as part of this, I've come to realize over the years is the idea that your core domain should have no dependencies. This might be completely obvious to some of you, but I'd like to bring it up as a separate point because this is where all the niceness starts, basically. You have some problem that you want to solve, and of course it will have a database as a backend. Usually you will have some graphical user interface, it will talk to the internet or to your file system and so on. But basically before all that, you have some core central problem here, your core domain that you want to model and map out and solve. And that one basically doesn't have all these gnarly, weird dependencies. And that's how a lot of these things turn nice, that we can do this. This is why we can have nice things when you do this with your core domain. Of course, this is not my idea. Here, for example, is from a blog post by Uncle Bob, Robert Martin, talking about the clean architecture, where you have exactly this. Now, the exact names of these layers and so on, of this modeling onion, are not all too important. The important thing is that you have your entities here in the middle. Those are the things that you care most about. And in a changing system that needs to respond to new challenges and so on over time, your entities will probably change the least, and they will be the most stable, and they were the reason you built your application in the first place and so on. On the other hand, stuff like databases or user interfaces and so on, by their very nature, they tend to change around a lot. They are not central to your application. They are quite important in their own right, but they come and go, sort of. Before Web 2.0, no one could predict Web 2.0, and so we didn't have the combination of UI and external interfaces that we needed for that. And 5 years later, something new will come along. And basically, your entities should be shielded and protected here in the middle from that kind of changing stuff in the background. So Uncle Bob Martin talks about a rule where it makes perfect sense to sort of shield the things here in the middle, and what you should try to avoid is to have something very stable have a dependency to something very unstable. So it would be wrong here to have the entities depend on the UI, for example. That's why we have the onion, and that's why we care about it and believe that it works out nicely. Again, the exact details here don't matter a lot. What matters is that we can do this trick called dependency injection, where the entities can still relate to the UI without being tied to it. We can still establish some kind of dependency injection here and talk about less stable things here in the inner things without tying ourselves too strictly to them. And basically, dependency injection is a nice technique for doing this, and a very well-established one, and one that we can do mindlessly and without thinking too much. I have a couple of examples of domains where I believe people have done this modeling and come up with more or less the perfect architecture or the perfect design. And as an obvious first example, we have domain events, which was a big game changer for me, thinking about business software in general, because it seemed to me that, okay, this view here of things was kind of idealized, and sure, you want to strive for that always, but how can you always guarantee that you can accomplish that? Well, it turns out that you can start modeling your core domain and your problem domain in terms of events, and that solves a whole host of things. So what this picture shows here is the core logic of that. You have your system here, and a command coming into the system. A command is simply a request for the system to change in some way. And the system decides, based on its current accumulated state and based on the validity of the command and so on, whether to accept or reject that command. When it rejects it, you get an exception back and the system stays as it was. When it accepts it, you get 0 or more events here, and the system sort of changes internally to accommodate for that. This leads to a really nice way of designing things. It solves a whole host of problems that are considered to be tricky and hard to overcome in software. It gives a really nice story for testing, where you can use these abstractions here with events and commands and exceptions to build out your tests. it solves inter-process communication and communication between different bounded contexts, where suddenly these events become a very clear signal about what happened in a bounded context. And interested listeners can sort of listen into these events and see them fly along. It solves how to persist data in the system, because these events are very persistible as well. We can do it with a normal MySQL database or other SQL database, or we can do it with a dedicated event database. But they are very predictable and easy to persist. Finally, we build up a kind of immunity to future change. By having these events, they are kind of eternal. We map out the event types once and for all, and then we can add new event types, but we basically never go back and change or remove any old ones, which are already deployed in production. But the way the whole system works here is that while we do that, while we sort of keep evolving our events in new directions, we haven't even started talking about how the central model works, how this system here and how its insides look. So it becomes kind of a macro version of this whole public-private thing that we talk about in object-oriented programming. Events being our public things, and this inside of the system here that we care the most about, our core domain, becomes the private thing. And so they are completely disconnected from each other, like a ball bearing or something. The insides here can rotate and change completely independent of the events here, and we have that guarantee that basically we can refactor this as much as we want. It's a really, really nice place to end up in, and basically it's hard to think of a business domain or some kind of problem domain that does not map well into this kind of thinking, where you basically have a system that changes in various ways, and when it changes, it emits these events and says, hey, I changed in the following way. There are a number of other clear advantages of this model as well. Maybe I should mention the biggest disadvantage is that you're sort of opposing yourself to the rest of the world by taking on an event-based view of the world, and so basically you have to do translation back and forth between your nice eventy world and the normal state-based world outside. That's sort of a cost that you take on when you do this. But you get a host of other advantages as well. It took me a while to realize that the reason that this model is actually really, really nice is that it's completely functional. It's a way to get functional objects in the sense that you start with an empty system here. That's basically an object that you just created with your constructor. And every time you go through this command generates event cycle and you build onto the system, you do some accumulation, you add to the end of this event queue. The system now has more events. That's exactly the same as saying as the object now transitioned cleanly, sort of functionally and immutably from one state to another. So these events, what they capture is these state changes that you go through with your system. And in a sense, all the things that we think are nice about functional programming and that we like from that world, we inherit because the events are basically functional transitions like this. And so this kind of model has become a little bit of a guiding star when I go into a new system and so on. We don't always end up on a pure event-based model. Sometimes we do, sometimes we don't, depends on the other requirements of the system. But it's been really nice to have this at the back of my mind sort of going into something. Sometimes just modeling things with commands and events really helps a lot. The next great example of a model that seems just right for what it does is Git. Now what's shown here is the different relationships between the three most common objects in the Git database, namely blobs representing the contents of files, and trees holding those blobs, and then finally everything gets tied together in individual commits. The takeaway from that graph is perhaps that we have unidirectional arrows pointing to simpler things all the time. So commits can point to trees, trees can point to other trees, or blobs, and blobs don't ever point to anything because they're just content. And so you get, on that level, you get some kind of reference tree here of simpler things near the edges. So that's just a technical way to describe what's in the Git database and how Git models the world. But what's really nice about this picture is when you realize what actually goes on with the computation of SHA-1 sums and so on, which basically bubble up these trees. You see there's a SHA-1 sum on each of these. First, every file content gets a SHA-1 sum, and then the whole tree and sort of the summary of its contents, all the blobs that it's pointing to, all the other trees that it's pointing to, also gets a SHA-1 sum computed. And finally, the commit contains some extra information like parent commits, who was the author, who was the committer, and so on, and various date times and commit comments. And all that gets stirred into the final content of the commit and gets a SHA-1 sum computed. Part of the niceness here is that it all happens gradually, sort of you add your files into Git, and this part happens, and finally you add some directories, and this part happens, and then finally you do the commit. So it's sort of a distributed computation of the SHA-1 sums, which is nice when it takes a bit of time for large files. But the real win here is that we've basically chosen a distributed view of the world. This SHA-1 sum here for the commit used to be a sequential number, where you could say, okay, this is commit number 5 in the system ever. The approach that Git takes makes that impossible already from the start. We cannot do that. If you're a distributed system, you could have programmers A and B working on commit number 4 and producing a new one, and they more or less at the same time, or at least without observing each other, produce commit number 5. And then we've already broken something, namely the global guarantee that in the system, commit number 5 means a single unique thing. And so SHA-1s have this fairly strong mathematical guarantee that when you see this particular one, it goes on for a while here, a total of 40 hex digits, it will be unique in your project, between all the developers of that project, but also on Earth, sort of, and for all of history, stretching backwards and forwards. That's a strong guarantee, and you might wonder, how can you ever safely make that guarantee? Well, you can't, but you can make it strongly enough, in the sense that these 160 bits that go into a SHA-1, they are fairly evenly distributed over a state space of SHA-1s, such that you would be hard-pressed to find a collision. Two SHA-1s having the same content but meaning different commits. Of course, it must happen because there's a sort of conceptual infinity of commits, and there's only finitely many of these SHA-1s. But the SHA-1 algorithm is good enough that it basically guarantees you no collisions. And there are various statistical comparisons that can be made there. The obvious one is you start flipping a coin with each hand, and you do that 160 times, and by some wondrous miracle, it gets the same result on both hands 160 times in a row. But our minds sort of break down there, so we take other metaphors, like you'd have to win the lottery 5 times on the same day and get struck by an asteroid or something, a meteor coming in. Or your team will have to be eaten by wolves, each person in an unrelated incident. And people go, but I live in Spain. Yeah, it doesn't matter. I once described these mathematical coincidences to someone in a Norwegian audience, as it happens, and some wise ass said, "Oh, so it is possible." That person was either a pessimist or a mathematician. But you end up in a very nice state here where, at least my mental model of it is, your whole project of commits is not a straight line anymore. Definitely not. It's a graph that grows organically from a single starting point, or a few single starting points. And just like in biology, with each of us is the potential sort of root node of a completely new subrace of humanity. All you need to do is go out on a desert island with someone and sort of start the new branch of humanity. In the same way, in Git, each commit is the start of a new adventure. You could go back at any point and start a branch there, start a new line of development. And that is possible because these SHA-1s here don't constrain you in any way. Third and final example of nice things. And we'll keep it brief here because everyone knows about this one. So UNIX Pipes. The original idea here being that Unix commands should do one single thing and do it well. And the power comes from being able to combine them, which in this case here means plugging sort of the input of the next command to the output of the other. And not only that, but they sort of run in parallel as well through some sort of green threading or whatever. And they can, when one of them blocks for some reason, one of the other processes can do some work and so on. This is very, very nice and has served the Unix people quite well. The model hasn't been exported to many other places, which is a little bit sad. The only real other contender I know about is PowerShell, which takes this idea and says, oh wait, it doesn't have to be text. It could actually be fully featured objects, and objects could go through this pipe, which actually sounds like a really nice idea, and could be the sort of one improvement of having everything be text always. Though Unix gets quite a bit of mileage out of simply being sloppy with these. Text can mean a lot of things. It could mean records and fields, or it could be just free-form text, or it could even be a byte sequence. It doesn't really matter. Of course, the niceness here is when we realize that all we're really doing here is plugging together some sort of relatively pure mathematical functions. So find here is a mathematical function, sort is a mathematical function, and unique is a mathematical function. And this pipe operator here in the middle is nothing other than functional composition. So again, the reason that this ends up being very nice is that it's clearly rooted in mathematics, and we can get a lot of mileage from that and use existing models, things that we know about set theory and functions and mathematics to make this really nice. Now we come to the second view, the slightly depressing one, where software development is not rational at all. And basically what we're doing all day is struggling against chaos and keeping chaos at bay. So this would be the top-down view, where already from day one, we come into a system where we have no idea what's going on. I thought that was a dialog box. Yeah, here we go. Oh, I think that was my LibreOffice dying on me. Hold on. Oh, it wants to recover a document. How about that? And we're back. And this precious timer that I set in the beginning, it's been lost. Here we go. So complete chaos. The code is no longer this nice black box kind of thing that we designed once and for all and we feel very happy about it. Instead the code is an organism, and we all know that about biology and organism, that the organism does what it damn well pleases in experimental conditions. And here's your mandatory cat picture. I actually went on Flickr to find a picture of a monster here to depict the code as organism. And what I found was this cat, apparently called Monster, posing over and over again in very cute positions. So that's why I got this picture. But the code can definitely be a monster. And it's not always the world's fault, it's sometimes our fault as well. We end up building technical debt. Anyone who's been on a even moderately big project knows that keeping the project clean and keeping everything in order and sort of keeping everything up to date and synchronized with each other becomes a project all on its own, and it sort of takes on a life of its own. And it feels like you do a certain amount of percentage of your time and your effort just keeping this nicely. I'm not saying that's wrong, because that's probably what you should do in a project, but it's one of these unexpected costs of just keeping everything nice and ordered instead of succumbing to this unavoidable mess. And then there's the other factor that we basically, either we built the system or we inherited it But there's a sense of we don't really plan for things to happen. Things happen to us, and the best we can do is measure them and see how things are and perhaps why they are the way they are. In other words, the system is doing what it bloody well pleases again. And it, in some sense, turns into less of a physical modeling situation where we have the system that sort of sits in an abstract space and behaves really well, and it turns into this biology situation where everything is messy and unpredictable, and we can't really say much about it until we actually observe it. And having observed it, maybe we can't describe it at all anyway. Maybe our sort of models are simply not enough for what's actually happening out there in the world and in the system. And the one keyword that I think differs in this view of the world compared to the nice and clean one that we just went through is that suddenly things turn into a resource thinking, and more particularly limited resources. Uh, we don't have unlimited resources, and it, in a moderately sized system that's actually doing nice production work, this turns into a problem fairly soon. We start hitting limits fairly soon, whether it's computational limits or network limits, or simply the good old-fashioned ones, limits in our own ability to understand what we're actually doing and what the system is actually doing. And so everything turns into a resource management in a way that doesn't show up in this nice and clean model that we discussed. I have a couple of examples here as well. They're fairly unrelated to each other, but they all sort of point to some sort of hopelessness in designing anything and things that can happen to us in the real world. The first example is where people do something rather bright, actually, in this situation. If you recognize that the real world is messy and we're not going to succeed in at any particular length in designing something ourselves, well, then you turn to things like evolutionary programming, and in this case, FPGAs, these programmable, field programmable gate arrays. And someone had the excellent um, idea to say, okay, let's just evolve this. Let's have a program sitting in a loop, trying out various components and plugging them to each other, keeping track of a score function, keeping a small population, and basically selecting on the elite that performs better than the others. When you do this, it turns out that it actually works out quite nicely. In this paper here, they wanted something like, I think it was a sine wave or a square wave or something. The details don't matter that much. But they got a system that actually did that. And some of these components here are unnecessary and we can remove them. So we remove them, and this is the actual functional system here. But the gray boxes here were the big mystery. They are functional parts of the system, but they are not actually connected to the system. So you end up with a situation where evolution sort of did what you wanted, but at the end, when you try to explain and analyze this system, it's unanalyzable and it's inconceivable why it does what it does. I guess there are physical sort of candidates for an explanation here. Resonance could be one of them. So these components here are sort of just sitting next to the main system and resonating in some way that makes it behave better. But the fact that this system is what comes out and that it's sort of the exact opposite of what we would imagine with conscious and deliberate design is kind of scary. It's kind of freaky that this happens. I'm gonna pull out a clock here so I don't just blindly. Okay, looks good. Great. Oh, and you have the minute signs as well. Excellent. Another example, and this is a story I heard from, I don't remember who, but it was actually at a Perl conference, an evening in a bar, where a company had this system in production, everything went fine, but every year in Argentina, a bug showed up, and only in Argentina, and completely, um, completely inexplicable until they actually looked into this. And those of you who have been in software for a while, you know what to think next, what to suspect next, and that is time zones and daylight savings and so on. Now it turns out Argentina as a country does something that almost no other country does. Maybe no other country actually does that. That is, they switch between uh, summertime and wintertime on the midnight mark. And this was Perl software, and they were using the very stable daytime library. And when you do that, and you don't particularly care about the time part, you only want the date part, so you leave the time part as 0000. A timestamp that actually doesn't exist on a particular day every year in Argentina. So the system blows up. And it was only through sort of rigorous testing and thinking really hard that they discovered this. Again, the lesson being that maybe we could have predicted this, but this is the real world sort of imposing itself on us. It's not us using nice rational mechanism to design the perfect system. This is something that definitely was a surprise and could surprise the best of us. Um, so I guess the lesson there, and in order to mention Perl 6 in a favorable way, thank you, is keep a separate date class. So you have date and then you also have date time. So if you only care about the date, you can use the date class, which is nice and much more predictable in other ways as well, because you've abstract away some of the weird things that date times do and only care about the dates. We have that in Perl 6 nowadays, and since many years back, much thanks to feedback from Rolski, the original author of the datetime library, and he said he regretted not creating a date class. So we did that. Third example, injection in SOAP-Lite. Now this is actually also a thing that really happened, and I took a screenshot here from the SOAP-Lite source code, and it's comment here about we need to protect against this particular thing here, and they even link to an article in a fracking magazine. I, I especially like that part, and sometimes I go back and read that article, which is really nice. Just to summarize it for you, you want to inject some code and run some arbitrary code on someone's server. You use this nice SOAP-Lite library, which is considered stable and well trusted and so on. And the SOAP-Lite library needs to dispatch on a particular method that comes in as input from the client, okay? So the method is foo, and you want to dispatch on foo. Now, Perl has this very nice way of doing that, which is you just put your input in a string, you put foo in a string, and then you use that string as the method call. Until you realize, or you're more likely your attacker realizes that you're not just limited to foo here. You could do something like other object : foo, and suddenly you're calling a method or a sub on a completely different package, a completely different class. And from there on, it's just a matter of finding some class or package that's already been included in the memory of this particular SOAP-Lite server running on that particular server, and exposing that for whatever two-argument file open that wasn't eradicated in some earlier. This is exactly what they did. I find it such a brilliant example of sort of a two-step exploitation of a system. Of course, now it's fixed, as you see here in the new regular expression here is making sure you can't do strange things like : But for a while there, you could basically take over a SOAP-Lite server by exposing this, and I think it's wonderful. And again, injection attacks, I'm not saying they're part of the environment that we can't do anything about, but they're usually a surprising thing, and we'll keep suffering from it. Injection attacks will keep being the biggest exploit on the internet until we realize that we should treat our sub-languages better than just being concatenations of strings. And in this case, just being unpredictable method names that could be more than we think they could be. So, yeah, there are a lot of unintended consequences in this second view. Actually, it seems like the systems at some point get driven by unintended consequences. And in some way, we come into work in the morning and we have no idea what to do, but the system will be bad and weird in various ways, telling us what to do with our time at work. So, okay, so who wins um, in this bifurcation of two views? Because now we have two competing views, so one of them must come out on top, right? And please, please let it be the nice one. Uh, Actually, I don't know, but my take on it is that we can actually make a difference by pushing the niceness quite far into a system. We can do a lot of upfront design. We can leverage these nice models that we talked about and get quite far doing that. We won't get all the way, and the reason we won't get all the way is that basically we're stumbling here on our own successes, and we're building bigger and bigger systems every day, and they will take on more and more of these unpredictable biologically inspired aspects until they actually come alive in some way. And if you want to know more about the endpoint of that, I heartily recommend this talk by Richard P. Gabriel about design beyond human abilities. Thank you. Um, the idea simply being that we're on the way towards designing systems or perhaps putting together existing systems that end up being so big that we simply cannot understand what we have built. There is no way. The premise of this talk is that there is no way. Um, of course, this could have already happened with the internet and so on. More likely, we're still trying to do this and succeeding more and more every day. But it's a very nice paper, and it's basically taking the view that there are some non-software systems out here that we can analyze to get a better picture of what we're doing to ourselves here slowly over the years with software. So we can analyze cities, we can analyze communities and so on, and see how they work internally and what kind of coping mechanisms they have and so on. And basically, the view that falls out is this one of a biology system, or we talk about homeostasis, for example. So the system has its own internal desire to keep itself stable and balanced all the time. Because if it didn't do that, it will fall apart immediately. But just like a living organism, the system is trying to right itself all the time. And also, the system is constantly operating under some sort of exceptional circumstances. When you have such a big system as this, something is always going wrong all the time, and we're sort of constantly fixing it. So yeah, the recommended paper. The end point of which is we need to be both physicists and do this nice modeling, and we need to be biologists and go chasing after our system in the lab and trying to catch it again. And this is what we need to do in order to handle both the beauty and the chaos of software development. Thank you.